In this half hour, I will go over the scope of the market for computing in automotive using artificial intelligence. I will discuss the evolution of the processor market in automotive from discrete scalar processors to massively heterogeneous platforms. I'll dig further into the differences between advanced driver assistance and autonomy and provide a forecast that highlights that there are actually two paths to autonomy. I will discuss how this market trend relates to the processor trends in relation to the dual path to autonomy and how this dual path is reshaping the ecosystem of how vehicles are designed, and conclude by bringing that all back to the processor supplier market trends. The word CASE is an acronym describing the trends driving the evolution of the automobile technology today. It stands for connected or connectivity, autonomous or autonomy, sharing or subscribing, and electrification. At Yole, we look at these trends, but today the scope will focus on autonomy and the growing trend towards artificial intelligence that is leading to the increasingly resourceful situational awareness by the vehicle. Vehicle technology is evolving to sense the environment at least as well as we can as humans in an effort to eliminate the most common cause of accidents, human error. Intelligence does not end at the advanced driver assist systems under the hood. It can include perceiving the responsiveness of the driver to further evolve advanced driver assistance. It can include inferencing data that traverses the edge to the cloud ecosystem as the market for automobiles evolves the market for mobility. As case trends dominate the OEM strategy for next generation cars, it also leads to the commercialization of mobility, leading to a different evolutionary strategy for developing autonomous vehicles. This can lead to slightly different semiconductor solution strategies depending on which evolutionary path you're dealing with. At many different stages, from the automotive edge to the automotive cloud, artificial intelligence software and hardware integration is evolving to adapt at differing evolutions. One of the most important automotive trends is the use of neural networking algorithms to enable real-time vision processing. We could spend days, and you will probably hear a lot more about neural networks in this forum, but the evolution of improving neural networking software algorithms has driven an evolution in hardware as well. The semiconductor industry is shifting toward a new range of processing architectures that rely on a combination of traditional scalar processing and massively parallel processing acceleration. Parallel processing commonly creates demand for FPGAs. The quantity of data that the advanced driver assist systems and autonomy has elevated to terabytes per hour. To handle this, the market is responding by evolving. Where once was general applications, now it is a general application and neural network. Workloads are including deep learning networks. In addition to precise floating point operations, accelerators must be designed to balance just the correct matrix of integer and floating point efficiency. Applications can still rely on well-defined and reproducible sequential routines, but to inference and learn from mass amounts of sensory data requires significant parallel and single instruction multiple data operations, such as multiply and accumulate, using a wide matrix and many transistors for each operation. In essence, the industry is not replacing the familiar scalar engines with their powerful cores for fast and versatile code processing and precise sequential task handling, but it is enhancing system performance using platforms and co-processing accelerators with the parallel processing to keep up with the massive data analysis. There are as many as 100 million lines of code running in a modern car, and most of that code is targeted to run on a scalar processor core using Intel x86 or ARM Cortex IP. The deterministic nature of a set of inputs driving a predictable and repeatable output is a necessary feature of computing everywhere, but especially in automotive. Scalar processors run through this code in a single or moderate number of threads at up to gigahertz speeds. Due to the various automotive safety guidelines, this code is rigorously tested, and its verifiable deterministic response is critical to passing government and industry standards for automotive quality and safety systems. Software is evolving to even allow scalars to improve performance running AI algorithms, but not at the scale required for autonomy. That being said, the non-sequential processing demands for working on extremely large datasets, such as inferencing based on the content of images and video, have led to an evolution in the automotive industry over the last decade to incorporate vector processing through the use of the ubiquitous graphics processor. NVIDIA was an early driver of this evolution, with its CUDA graphics cores being used for general-purpose vector equations. ARM Mali and Qualcomm Adreno have been later less energy-demanding entrants, gaining popularity through infotainment before addressing advanced driver assist. These vector processors were critical to exposing that vision processing could greatly increase the situational awareness, elevating automotive safety towards advanced driver assist systems. Today, the demand of energy-efficient vision processing has led the industry towards more efficient big data processing solutions based on matrix processing algorithms. In advanced driver assist systems, this has led towards platform and accelerated solutions that add logic specifically crafted to accelerate neural networking algorithms through matrix processing logic acceleration. With a number of different architectures, from Xilinx UltraScale Plus or Versal, Intel Mobileye, NVIDIA Xavier and Orin, Toshiba's Visconti, Renesas V3H, NXP S32V, and CalArray, MPPA, and others. As I alluded to early in this presentation, different motivations can lead to different evolutionary paths toward vehicle autonomy, as well as different progression rates. The automobile market for the standard consumer is a strategy of making our existing automotive product lines progressively safer. Perfect may be the enemy of good enough, for OEMs striving toward autonomy by making each generation of automobile smarter, more efficient, and safer than the last, with an overall strategy of design that incrementally evolves each electronic control system as well as the overall network and centralized intelligence. These advancements are driven by the competitive landscape, approaching 100,000 passenger cars and light commercial vehicles annually. Commercial mobility companies tap into the availability of light commercial vehicles while simultaneously developing solutions that are more directed at evolving the overall mobility market with an eye on the new concepts of mobility, from robotaxis to specialized commuter transportation to integrated mobile logistics. For OEMs, incrementally improving automated driving, vehicle safety, and all forms of situational awareness means investing in a variety of solutions and getting to market with improved performance each generation. This has led to a wide variety of vision processing solutions, as well as increased volumes of cameras and other sensors. For mobility markets, especially mobility as a service, they can piggyback on developments of traditional OEMs for fleet vehicles while attempting to reinvent the overall function of the vehicle. In the mobility as a service strategy, reaching full autonomy means reinventing the vehicle. For now, most OEMs are approaching autonomy through the NHTSA autonomy stages. 1 includes driver control with some automated assist. 2, partial automation with some integrated automated assistance control, but the driver still must remain engaged at all times. 3, conditional automation where the vehicle is functionally autonomous under normal conditions, but the driver must be ready to retake control at all times with notice. At 4, high automation, where the vehicle is fully capable of all functions without the driver engaged, but only in certain conditions that could include designating the locale or visibility limits. Driver engagement is optional at this stage. At level 5, we reach full autonomy. As autonomous vehicle technology progresses, the personal car and light fleet vehicles OEMs require a design that is appealing and functionally consistent to current vehicles in design to be marketable. For the OEM, this means keeping all the same functionality while making systems smarter and more integrated. At level 1, this strategy was dominated to include integrating vision systems for specific functionality, such as separate forward-facing cameras, parking assist cameras, surround view cameras, and more. By level 2, the technology requires greater integrated functionality. It is increasingly relying on new sensor data to achieve results while it advances through levels. Most of the industry has tacitly agreed that level 3 is impractical due to human attention limitations and liability issues. By level 4, there must be a central domain controller with or without pre-processing AI assistance. The complexity to adjust to the edge conditions required to move from level 4 to 5 will be computationally intense, and current development indicates high-level compute performance with extremely well-integrated sensor environments will be necessary and costly in many ways. For mobility as a service, the competitive landscape requires replacing the classic vehicle ownership model with a connected edge mobility device supporting that service. It is essential to focus on the centralized compute platform environment immediately and partnering with processor suppliers that are focused on full autonomy now. To better understand why there is a significant difference in the evolution of AI development for autonomous vehicles, we must consider the two different driving markets and how they approach development. For the OEM, the process is about adding improvements to the existing automobile that complements the existing systems, while incentivizing drivers to continue to pursue these vehicles because they are safer and more convenient than prior generations. As an example, the manual braking system still exists, but evolves with an SoC controlling automatic emergency braking to override brakes. Other electronic control units, such as traffic jam alerts or lane keeping assist, include more sensors and processors dedicated to their function to add incremental driver assist, leading toward autonomy. As the demand for AI increases, it becomes more efficient to move toward higher performing processors and accelerators to orchestrate the many sensors input into a more centralized domain process, and ultimately platform solutions with even greater cost, area, and power efficiency. We predict many stages of development as the number of electronic control units gets reduced, but the increasing interfacing of sensors leading towards more sensor fusion and greater platform solutions increases. Research and development from mobility as a service perspective is not as concerned with driver assist. It starts with the assumption that autonomy is the goal and focuses on developing a central domain controller or even data center server in the vehicle to control everything. Cloud services and infrastructure connectivity are critical to the business model for success. For this reason, training starts from a mobile computer perspective, and many existing systems in vehicles are redundant or superficial. Once the software can accurately achieve situational awareness to level 5, then the robotic vehicle developer redesigns the car to accommodate what is needed by the centralized service business model. For mobility as a service, autonomy may disregard stages of relying on individual SoCs with AI, but individual safe scalar controllers and sensor fusion will be no less critical to the centralized AI domain controller. Neither OEMs nor mobility as a service developers see a strong strategy toward marketing vehicles as L3, giving drivers the impression that it is okay to remain disengaged but ready to take control with notice. Instead, as the technology continues to develop, many OEMs and top automotive tier suppliers have taken to marketing advancing ADAS technology with greater sophistication as 2 plus and further 2 plus plus to avoid the trap of promoting the driver's ability to become disengaged from driving. Rather, advising that the driver can take their hands and then eyes off driving but remain engaged is how these designations progress. The graph provided here shows the layered approach that Yole estimates for vehicle sales with the stated level of autonomy. As shown, 2020 and 2021 are heavily impacted by the COVID-19 outbreak. Later estimates have shown that the actual figures are slightly less drastically depressed than estimated here, but the trend remains. As the latest technological advances are introduced into luxury vehicles, SUVs, and performance cars, trickling down to mass market vehicles, we are already seeing strong markets for L2 plus shifting imminently toward L2 plus plus growth. While there could be a few L3 vehicles introduced before 2026, the vast majority of OEMs will migrate through L2 plus plus in the mass market toward L4 as introduced in luxury platforms growing by the end of this decade. The next decade will then be dominated by L4 becoming mainstream and L5 introductions, which should coincide with the rise of mobility as a service competition. By the 2040s, autonomous vehicles will be the norm, and mobility as a service will take an impactful share from traditional car ownership, leading to a decline in personally owned vehicles. So why is this trend important here at Xilinx Adapt Automotive? For all of this autonomy to be realized, the computational performance of the automobile is going to explode with AI processing demand. Yole expects artificial intelligence-based image processing and context analysis to demand as much as 67 million units of processors for advanced computing of AI for advanced driver assist by 2025. This represents a continuous average growth of approximately 132% or more. While currently we are seeing a trend toward one AI-enabled processor per camera at L1 and L2 systems prevalent today, there are few use cases for full domain control or various sensor fusion systems. But in order to progress from L2 to L2 plus to L2 plus plus and ultimately L4 and L5 system, the advanced driver assist systems will require the ability to coordinate all of the disparate electronic control units and sensor data. Other functionality will become even more critical, such as memory access, latency, security, and adaptability. While this may play out with several layers of intelligence and to optimize performance, ultimately advanced driver assist must adapt to platform solutions capable of integrating all the data the vehicle can provide to become situationally aware enough to maintain autonomy. These platforms already exist in the form of multi-chip platforms for vision, acceleration, safety controllers, sensor integration, or they can be massively heterogeneous SoCs and adaptive compute acceleration platforms such as the Xilinx Versal. What is clear is that the classic scalar processors traditional to automotive market will still be needed for safe control, but the intelligence required for autonomy is going to require neural network processing, and that is going to represent a processor evolution. At the top of this graphic, we look at the introduction pattern of the key driver assist functions along the path to autonomy and the number of AI-enabled systems on average. This includes automated emergency braking, adaptive cruise control, lane keeping assist, parking assist, traffic jam alert, driver monitoring, to mention a few. These lead to domain controllers that are massively heterogeneous platforms and ultimately autonomous platforms. As advanced driver assist systems develop, so too does the reliance on more sensors to improve the situational awareness of the vehicle. This evolution is based on software in the form of improved neural networking algorithms, improved sensor data to feed those algorithms, and the processing strategy to bring them together. Beyond the GNSS receiver, motion sensors, temperature sensors, we see a growing market for radar, multiple application-specific cameras, LiDAR, and likely integration of networking data from vehicle-to-everything systems. As the technology progresses, sensors and cameras increasingly network together higher levels of AI integration. Advanced driver assist systems and autonomy algorithms advance from basic inferencing to highly integrated deep learning algorithms with an even increasing number of subnetworks or layers. These more complex deep learning networks demand increasing operations per second, lower latency, and aggressively increasing memory for greater data quantity and quality feeding the AI application. In terms of the processor evolution, vehicles still have considerable constraints in terms of power management, longevity, safety, cost, and software ecosystem. The dominant processor for automotive, the MCU, will likely always be needed for reliable control and actuation of physical systems. Safety. But vision computations are already beyond their capabilities. Vision processors can be either integrated subsystems in automotive-specific SoCs along with dedicated graphics or addition of discrete accelerators, or configurable SoCs. Ultimately, to get to L4 or L5, individual electronic control units must give way to domain controllers with large heterogeneous platform solutions. As discrete processing solutions evolve in this direction, FPGAs are already embracing these demands, integrating application cores, real-time cores, vector graphics acceleration, control engines, and even configurable logic to address parallelization and sensor fusion in solutions like Xilinx UltraScale Plus. To get to L5, we anticipate the need for platforms like Versal to address the increasing demand for heterogeneous processing, AI acceleration, and sensor fusion. The trend toward autonomy is not happening in isolation of other trends in the automotive industry. The advanced driver assist systems and autonomous driving strategy also have to adapt within the other key trends affecting automotive. Software and IP for autonomous driving is constantly being developed by OEMs, tier suppliers, software and IP developers, each having different strategies and motivations towards autonomy. These business models may include other services such as infotainment, connectivity, and other services. As OEMs continue to advance the levels of AI through advanced driver assist systems, their serviceable market is much larger than that of their mobility as a service counterparts. But the margins are tighter as they compete with a full range of existing vehicle models. Conversely, the mobility as a service market is considerably smaller, but due to the focus on autonomy and cloud services, the platforms and their ASPs are considerably larger. The trend toward electrification has a strong impact on the evolution of vehicles and infrastructure. The L5 autonomous car of the future is very likely to be fully electric and need to include data regarding the health and status of the electric powertrain and battery into its functionality. The point of addressing these different market influences is that as the business model for owning an automobile begins to lose share to mobility as a service, all of these current influencers will have to adapt to it, and that includes semiconductor suppliers. As autonomous driving moves away from large numbers of discrete electronic control units towards a domain controller, It is clear that the platform providers will be more successful, playing a bigger role in providing the software stacks that accelerate AI development and sensor fusion in their stacks. This greater role also brings them more closely engaged with the OEMs themselves, rather than traditionally being only engaged with the Tier 1 providers. That being said, it is not to say that Tier 1 providers are being circumvented, only that there are more lines of communication and direct feedback as software and stacks become more integrally associated with specific platform ecosystems. While all OEMs will have resource to develop AI solutions, the relationship they choose to engage with the semiconductor suppliers typically is driven by the complexity of the autonomy that drives up the investment, balanced with how much they can invest in further outside services. While some OEMs will assume a go-it-alone methodology of AI development to control all aspects, the vast majority will embrace developing on platforms with significant software stacks provided directly from the processor suppliers, or some will engage specialist third parties to optimize a solution based on the desired platform. To conclude, we see the autonomous vehicle ecosystem trends are splintering the market into two business models. The dominant industry for now and for a long while includes the traditional OEMs designing cars that are safer and more convenient for drivers, and will evolve into the autonomous vehicle that is still the personal extension of a vehicle owner's comfort zone. The OEMs are increasingly engaging directly with processor suppliers to strategize about the evolution through various levels of driver assistance toward full autonomy. The second industry is the mobility as a service industry that seeks to both physically and culturally evolve the autonomous vehicle market into one where consumers are satisfied with the convenience and a cost-saving model over ownership that requires developing vehicle autonomy as part of a cloud and infrastructure that does not require the evolution of driver assistance, but rather focuses on the end goal of driverless ecosystems. These companies are engaged more heavily directly in developing the situational awareness required for a full autonomy with less concern about adapting to current design restrictions. Semiconductor suppliers will need to engage both ecosystems on the level of playing field that most suits their end game, but in both cases, deep neural networks and increasingly complex sensor fusion will likely play a major role in the solutions that drive these markets forward. To summarize the technology trends, even the 5 levels of autonomy are evolving into intermediate levels, currently L2 plus and L2 plus plus. Autonomy level 3 is a liability. Regulations and standards are poor, so most OEMs will skip L3 and move directly to L4 or 5. Advanced driver assistance and robotic vehicles are different markets as ecosystems. The technologies, average selling price, objectives, and business models will vary. The entrance of artificial intelligence and neural networking algorithms are directly responsible for rapidly increasing demand for integrated and discrete accelerators, memory, and improved sensor systems. For many years, AI has been using GPUs to offload the neural network. As the fusion of multiple inputs increases and deep neural networks become increasingly complex, a combination of GPUs and neural networking accelerators in the same SoC or vision accelerators as coprocessors are supplanting traditional GPUs for AI development. To get to the performance needed for level 4 or 5, vision accelerators may not be enough. High parallel solutions with the ability to adapt to different fusion strategies for sensors, as well as data from infrastructure and cloud services, will gain traction, especially in mobility as a service. Platforms will increasingly take share from discrete AI accelerators. In the end, solutions like configurable SoCs and platforms from Xilinx with highly parallel processing for deep learning and adaptability for sensor fusion strategies are well placed in the market. GPUs are replaced by vision accelerators and ultimately heterogeneous platforms as advanced driver assistance progresses towards autonomy domain controllers. Neural networking software should be the focus for success. Silicon providers should also engage in collaboration with Tier 1 OEM and software solution developers to provide these platforms.